Okay, so this section is about design for test miscellany. It's miscellany because you'll find that it is not as structured as what we heard this morning. It's about miscellaneous ideas and thoughts around design for testability, how we can incorporate some of those ideas into our specific environment. You'll find that if you lift those ideas as they were, structure design for test, LSSD, or scan design, or even built-in self-test, and try to implement it in DEC environment by brute force method, you will soon find that nobody likes you, and in fact, you will yourself find that it cannot be justified yet. So this idea, this presentation is going to be a mixed bag of ideas, and please bear with me if you find that it is not as structured as it could be. So let's begin with design for test for special functions, some of the things which we may have missed out in the morning. Let's begin with random access memories. Random access memories are very special. None of the schemes presented in the morning fit very well for random access memories. That's because RAMs have unique failure modes. So here are, here is a small list of various failures we can find in random access memories, such as address uniqueness, cell, row, or column disturb. That is, while you're reading one cell, other cell may get affected. Data sensitivity, which is also somewhat related to the previous one. Read-write recovery, whether when you read one cell and try to read the next one, can you do that fast enough? And same thing, the address switching speeds. So if you try to test those things with pseudo-random vectors, as we do with built-in, with Balbo type of techniques, you'll find that we may grossly fail to get reasonable coverage of this kind of failures. So what you have to do for random access memory is to use special RAM pattern tests. These are algorithmically generated tests such as checkerboard or march or moving pattern inversion, Galpat, or paragons. Now these are all, each one of these is designed to go after a specific set of failure modes listed here. Now we don't have time to go into the detail of those, but the problem arises if you wanted to, trouble is all these tests run for too long, and your problem is compounded if the RAM is embedded in logic, and then it tends to chew up a lot of testing time. Plus, you may not have enough access to the memory when it is embedded to apply those patterns. In those situations, what you may want to consider is self-test for the RAM, and the way to do is shown here diagrammatically. Only thing we need to add to the RAM, basic RAM, is some kind of address generator which will generate addresses to provide this kind of testing, a pattern generator, again pattern to provide march test or a galloping ping pong or a paragon, and something to check the responses coming out of RAM, and a controller which will control the algorithm to be applied. It is interesting, even though these are different names and these algorithms differ from each other quite a bit, but when it comes to hardware, we can apply essentially any of these patterns with fixed set of hardware. It all depends on how we drive the controller. Okay. In fact, we can come up with a standardized programmable controller with something to program which kind of pattern we may want to apply. But other than that, rest of the hardware remains the same. Now one may ask, what is the cost of all these things? Good question. Here is a study I had done several years ago, about 4 years or so ago. And that time I wasn't too smart. Now I know much better way to do all those tests. But this shows number of transistors added versus number of words or your RAM size. And as you can see that For let's take a case of 1K RAM, okay, and this is for the dynamic RAM. We have several curves here because this is a 1 bit by 1K RAM. This one here is, I think, 32 bit by 1K RAM. I'm sorry, it's the other way around. This is for the 32 bit by 1K RAM, and this one is for 1 bit by 1K RAM. So for a good size RAM, we can see that the cost is in the region of 2% or so added transistors. And as I said, this was done when I didn't know how to do it good. If I were to redraw this again, the curve would be somewhere here. So the next special function we consider is ROMs. We use a lot of them. And ROMs really fit very well with the linear feedback shift register scheme covered this morning. Typically, we have ROM either built into the system or on the chip for providing some kind of a microcode. And we have some kind of microprogram counter driving the addresses to the ROM, and some kind of a micro instruction register getting the words coming out from the ROM to be supplied to the rest of the system. Now, this is where we can bring in our built-in self-test very easily. What we need to do is just replace those two registers, counter and the register here, with linear feedback shift registers. The one here will generate addresses and apply to the ROM. And as the words come out, we can collect the signature by the one on the output side. In fact, we don't really have to have a linear feedback shift register generator here. You could use the microprogram counter, which may be already there in the system, to drive the addresses to the ROM. And as you are reading out the ROM, you could be collecting the signature. So instead of looking at millions and millions of bits of ROM, you could be just looking at the final signature to determine whether the ROM is OK or not. What about the PLAs? We use lots of them, especially in the custom chip environment. The problems are that they are usually deeply embedded and highly sequential machines. Further, they are associated with them are a large number of inputs and high fan-in. And as you may recollect, when Roy mentioned this morning that if you have a large number of inputs and high fan-in, then pseudorandom vectors tend to fail. Those are, the failure modes over there, your faults become random pattern hard. That's because supposing you have a massive AND gate with 20 inputs, to get the stuck at 0 fault on the output, stuck at 1 fault on the output, what you have to, stuck at 0 fault on the output, the pattern you have to apply at the input is that all inputs must be 1. What is the probability of getting this test vector in a pseudorandom test sequence? It is usually 1 in 2 to the minus r, where r is the number of inputs you have to feed. So those kinds of problems make applying built-in self-test, straightforward built-in self-test, a little bit difficult. Further, because of these previous problems, automatic test vector generation is also difficult. So the solutions are, well, we'll come back to this. Let me skip that one. We can do self-test, reasonable self-test for PLA by using a nonlinear feedback shift register, which will get all stuck-at faults as well as shorts. Further, the test vector set would be independent of PLA programming. And of course, you won't need any test vector generation or even fault simulation. To explain this, I'm going to use two view graphs here. See, what is a PLA? Basically, it is a NOR array, AND plane and OR plane. Both of them are, especially in the MOS world, they are both NOR planes, okay? If this is a NOR gate, to test it for stuck at 0 and 1 faults, we have to apply this set of inputs. Supply all zeros here that will get stuck at 1 faults on each one of these layers, as well as it will get stuck at 0 fault on the output lid because the fault-free output is 1. To get this stuck at 0 fault, we shift a 1 through this input. First we apply, let's say, 1 to this input and keep remaining inputs at 0. So by doing that, we would be sensitizing this path, and we get stuck at 0 fault on this lead, as well as we'll get stuck at 1 on that lead. So basically, to test out the test vector set for PLA we don't need anything fancier than this shifting 1 test vector. And that can be very easily obtained by putting a non-linear feedback shift register. Now, what we talked most of the time this morning was linear feedback shift register, and they are usually capable of providing all input combinations, but we don't care for that in this particular case. We just need shifting 1 test vector. Now, in addition to that, okay, see, this here is a NOR plane, and here is another NOR plane. So we already sensitized the faults here by shifting in a vector of 1 here, by shifting in 1 through this shift register. After doing that, we have to sensitize the faults to the output where we can really detect the faults. So for that, we have another shift register over there, which what it would do is sensitize 1 output line at a time, and you apply that algorithm repeatedly. Too bad that I won't be going into the detail of this, especially now. This slide was done several months ago. There is even a better way to do it. Now, there is another special function which I hate to tell you that I don't know anything about how to do design for test, and that is the analog functions. But going through the expectations of people here, nobody said that they cared too much about analog functions, so I think we are in good shape today. So the next topic I want to cover is called how to make design for test affordable. So let me go back to this for a second. When it comes to design for test, this is what most of the people view design for test as. Too fat, not enough room on the functionality express. And the guy always gets left out. Okay? Let me tell you one secret. If you were to travel by train in India, this is what most of the time the scene is, But the secret is that there is always some room on the board. Only thing you have to do is force your way in. Okay? So this section is about how to do that. In fact, if you don't throw anything on me, this is what I would like to convey by this section. Okay? All right. So the first thought is, remember in the morning we talked about every time we want to test something, we self-test something, we sandwich it between 2 linear feedback shift registers. Now those linear feedback shift registers are really expensive, very hardware intensive, area intensive. Question is, can we do something about it? Can we get by just using 1 of them? And answer is, yeah, there isn't anything in the world which says that you cannot do that, especially if your function under test together with linear feedback shift register satisfies the property of propagative randomness. What it means is, remember when we had the another linear feedback shift register here, it was providing pseudorandom vectors here. Now what if this function under test, when we apply a pseudorandom vector here and look at the output at the other end of the linear feedback shift register, this is the data compressor. If this vector itself has this randomness properties, why not use it like this? And a lot of people have used it, and they find, in fact, our own BIIC has self-test done in this mode. But the problem is, how do we determine the fault-free signature or even how do we determine its fault coverage. You need fault simulation, and at that time, these things may complicate it. However, it doesn't have to be always bad. For some special cases, you will find that this is a perfect thing to do without much of a problem. And one example of that is data path. Excuse me. Okay. Now, data path, what do we have usually? Some register file, some ALU. Can we think about putting one linear feedback shift register over there, which will provide pseudorandom vectors to this functionality to be tested, and also look at the responses and obtain its signature? Now let's analyze this one. Now registers, they readily satisfy propagative randomness, which we talked about. That means we should be okay to use built-in self-test. Also, make an observation that for an n-bit register, if you just apply n plus 1 pseudorandom vectors generated by linear feedback shift register, you would have got most of this tucket and also adjacent short or the bridging false. To illustrate this, let me show you what a pseudorandom vector, pseudorandom pattern set looks like. So here is a 5-bit pseudorandom vector set. You draw a line with, you take any 6 of them. You will find that you'll make 2 observations, that every bit position has flipped at least once if you take 6 of them, okay, for a 5-bit LFSR. Also, bits in every pair of bits here would have been at opposite polarity at least once during these 6 vectors. That means they are good enough for testing a register. Okay? What do you want to apply to test a register? Write a 0, read it back, write a 1, read it back. Okay? And we would be able to do with these vectors. Also, so that takes care of guaranteeing the effectiveness of the test vector set. What about predicting the signature? Well, that is also easy, especially if you keep the sequence of operation fixed. That is, you pick a register, write a pseudorandom vector, read it back. In other words, when I say read it back, I mean read it back and obtain, compress it, let it go to the signature. Then whatever is the state of in this signature register or LFSR, put it back into the register, read it back, generate the next state, and put it back. If you do like this, this is what happens. If this was the original test sequence with the linear feedback shift register ran in autonomous mode, when we run it in this mode, this is what happens. Let's say we start out with that vector. We put it in this register under test, and we read it back. By doing so, we will jump, instead of getting that pattern, we will jump to this pattern here. This is, by the way, this is what the pattern looks like in this particular mode. All right, so we jump to this vector, and then when we compress this vector again, we jump here to the pattern number 5, and then next time we go to the pattern number 23. So we still get exhaustive test vectors. This is the exhaustive list, but it is modified, okay? So our effectiveness is still in place, but the fact I want to impress upon you here is that we don't need false simulation to find out what would be the final signature of testing like this. We could predict it analytically or by just counting. Okay, so that takes care of this part here. Now what about ALU? Can we apply similar trick to ALU? And answer is yes. If you just perform simple operations which pass the arguments like A plus 0, A minus 0, A and 1, B or 0, things like that, what you would have is the response vector is same as the input vector. Now, if I did an experiment the other day. I ran a fault simulation by doing this kind of operation on a 16-bit ALU, and gosh, I was surprised. By just about 200 vectors or so like that, I was able to get 90% stuck at fault coverage. Of course, the remaining 10% may give a lot of problem, but here what we are trying to do is trying to get as many things, as many faults as possible, as cheaply as possible. One linear feedback shift register, and we would have pretty good coverage, nearly 100% coverage here, and 90% stuck at coverage here. The next issue is that PolyDiv built-in self-test and serial scan registers, they seem to be made for each other, because you remember in the morning Roy showed examples of how LFSR and test point flops are made. In other words, what I'm trying to say is they have structural affinity. Linear feedback shift registers are made around test point flops. Also, in both cases, we don't like races, hazards, and indeterminacies. Remember, one of the fundamental rule of signature analysis is that your signature must be unique. Signature of the fault-free circuit must be unique. And in order to guarantee that, your circuit should not have any races, critical races, or hazards, or even indeterminacies. Now, they can both help each other in several ways. For example, scan design can be helping PolyDiv self-test for initializing the linear feedback shift registers. Or, if after obtaining the signature, you may be able to use the scan path to dump out the signature. And PolyDiv self-test can also help scan design if you have a serial scan design machine. Instead of storing all those serial data on disk, you could be using a linear feedback shift register to load the scan path. Here are some examples along those lines. So if this was our original design with original scan designed logic, we could be using a linear feedback shift register here to load the test data in. Another one on this side would compress the data as it comes out serially and obtain the signature. An extension of this idea, IBM calls STUMPS, which stands for self-test using MISR and shift register. I think Roy forgot to mention you that in this field, there is ample opportunity to give names, okay? That PolyDiv was one instance of that. Now here is STUMPS. So what we have is here, we have several scan paths, and they may be on different chips or modules, and they may be all driven by parallel bits of a linear feedback shift register. And again, in the end, they may go to a common signature register to obtain one signature for the entire system. Now, at this point, you would be able to determine go, no-go status of this system. The next thing you want to do is find out where the problem is. You isolate the fault to a replaceable module or a replaceable chip. In that case, you have a bunch of enables and disable lines here. What you could do then is disable all the inputs to this linear feedback shift register, select just one, and obtain this signature for this device here. And that way you would be able to go, again, you still do the self-test, but you would be able to isolate to the repressible unit. If you have any questions, I think it is all right to interrupt. Now, again, I want to point out that test point flop is the key element in this design for test techniques, whether we are doing external test or built-in self-test. In fact, the cost of your design for test approach is directly related to how efficiently you can implement this test point flop. And if you were, I don't know how many of you here have to do MOS design, but what I'm going to show you in next couple of slides is an idea for implementing scannable flop in MOS, and I call it system latch scannable flop. First, let's see what are the various alternatives so far. Now, if your design is a double latch design, by that I mean if you have you have flip-flops surrounding the combinational logic. That is, just imagine that we have a combinational logic here, and we have a flop at the input of it, and another flop at the output of the combinational logic. In that case, scan design is very easy to implement. Scan or even linear feedback shift register-based self-test. Okay, I will just whatever I say here is also true for built-in self-test, but for the sake of simplicity, let me just concentrate on scan design. Okay, so if we have if our design is a double latch design, to convert it into scannable design is very easy. We just have to add a multiplexer in front of the flop, and we got ourselves a test point flop and an easy to implement scan design. So the hardware to be added here is only to the extent of adding this mux. But most of the designs in DEC, especially in Hudson environment, are only single latch design. That is, we have only one latch, only latches surrounding the combinational network. Now here, if you want to implement the scan design, you not only have to add the mux, but you must add a whole slave latch. Now that's a lot of hardware, and no wonder designers don't like it. Now on top of that, there is a limitation of test operation. So that is explained in the next slide. So let's say the way we operate is we shift in okay. So what we'll do, we'll shift in our test vector. When we do that, we will have here the test data ready to be applied to this circuit under test. We'll have test data sitting here, which is ready to be applied to this circuit under test. The next thing we want to do is go back to the system mode. We apply system clocks once in order to generate the result or the response of this test vector. Let's say we apply system clock B first, okay, in order to get the response of this circuit to the data here. As soon as we apply system clock B, we get the result here all right, but we destroy the data which was waiting here to be applied to this circuit under test. So in order to test this circuit, what you have to do is you have to shift in the same test vector one more time, but this time you apply system clock phase A first, and then apply B and scan out. So that's a little bit of complication, no big deal. I agree, okay? If that is the case, you may wonder why not implement scan design as shown here. If we have two latches clocked by different clock phases, A and B, why don't we, during test operation, why don't we operate this one as a master latch and this one as a slave latch? That would work perfectly all right, except when this picture is deceiving. What I have shown is only one latch is clocked by one latch over here and another latch over there. But usually what we have is array of, or these latches occur in clusters. You may have a register here clocked by phase A and another cluster over here clocked by signal B, clock B. For example, take this PLA. I was looking for this slide, but couldn't find it. It's in the wrong place. All right. See, usually we consider the example of PLA where we have some latches at the inputs and outputs. If you were to scan those latches, as I told you, this is what you may end up doing. Make this one the master latch, find its slave latch on this side, then come back here. This one is your next master latch, and go back here to its slave latch, and so on and so forth. This is how you may have to chain it. And look at that. It is very wire intensive. So what has been found is this new thing called system latch scannable flop, abbreviated as SLSF. Assumption is that, let's say, to begin with, you were to implement your latch as shown here, where we have a static latch with 2 inverters and a feedback path. We modify this original latch by adding 2 transistors. During the normal operation, this transistor is on and this one is off. Now, during the test operation, we turn off the system clocks, this as well as that. We operate the test clocks T1 and T2 in a non-overlapping fashion. By doing so, what we will have is master-slave dynamic flop. There is a master latch formed by this transfer gate and this inverter. This inverter has a input capacitance. That's what makes it dynamic master latch. And similarly, we have the slave latch here formed by this transfer gate and this inverter. So at the cost of 2 transistors, we could have a scannable latch. Now, now we should be comparing what is the advantage of this scheme over the previous scheme. Whereas we had several wires going back and forth in this implementation, over here our scan path is nicely going in one direction. Now here is some timing detail of how this operates, but well, it's very simple. During normal operation, you use your A phase system clock A and B in the normal way. During test operation, first thing we want to do is shift in the test vector. That we do, we turn off the system clocks, as you can see here, and we use T1 and T2. We shift in the test vector. Then we want to capture the response. So to capture the response, we activate system clocks. All system clocks can be activated at the same time. Okay? And then we shift out the result by going back to T1, T2. Now here we have to do this shift operation. We have to shift in each test vector only once, as against in the previous scheme we had to do however many phase clocks you had in your system. So that is the advantage. Okay. Let's see. Now here is where real unstructured portion begins. How do we implement testability in DEC environment? In fact, this is the portion I would like to make interactive, because I don't know everything about DEC environment. So some thoughts are here. At the system level, what we want to do is set testability goals for the entire product's life cycle, and then specify testability requirements at each level of assembly. This is really philosophical. Okay, we'll see some specific examples. And then, having determined the testability goals, we should develop a global test strategy. For example, scan design, built-in self-test, or a combination of scan design and built-in self-test, and try to address as many of the goals which we may have set here as possible. And at the next step would be to integrate this global test strategy into the system architecture. Now, important of this step is, see, if you were to add something which would only do testing, it would be viewed as luxury by designers. So the goal here is to salvage as much of the system hardware as possible for test operation, or for the testing function. So that's what we achieve here. So having done that, whatever is left out, we should try to implement those test hooks on individual boxes and chips, such as iBox, eBox, or individual gate arrays, whatever the case may be, or with a set of testability support chips. Sometimes, you'll find that particular box is so crowded that it cannot take any additional test hardware. And test hardware must be implemented outside that box. And in that case, the test hooks may live as testability support chips. Now, there are two examples in DEC which have taken this kind of system approach. Titan is one, and Aquarius is going in the same way. Let's consider implementing testability at the board level. At the board level, we can see two types of boards. One I would like to call intelligent boards. Here the characteristics are that these intelligent boards are bus structured, and they are usually populated by CPUs, RAMs, ROMs, some communication ports, etc. In fact, this is what typically the world is in low-end area, low-end people. Now try to implement brute force, scan design, or even built-in self-test in this area, and you'll soon find that you really don't have a good answer. So what about the strategy here, what I can say is that BIST is certainly more appropriate than scan design. Incidentally, we also have off-the-shelf components over which we have no control. So built-in self-test may be more appropriate than scan design. And what you may want to do is perform intelligent test with CPU in the test loop. In fact, I could almost state a little line here that intelligent things require intelligent tests. So one approach would be to keep the CPU in the test loop and maybe add some diagnostic ROMs, polydividers, loopbacks, etc. Now, this is what we were doing yesterday, and I think for some time to come, this is what we may have to continue to do. However, there is one example from literature called microbit, where they tried to implement linear feedback shift register for the intelligent board. It was an 8085 based system with all those things I mentioned on the board: RAMs, PROMs, displays, some communication ports, etc. In addition, those people, this is, by the way, example from Siemens, they added 2 linear feedback shift registers at the board level. One to provide the test vectors, other to capture the responses. And by doing so, plus in addition, they had some test code sitting in this PROM. And these are, by the way, loopback features: serial port loopback, and that one is the parallel port loopback. So with the help of those 2 linear feedback shift registers, they claim that they were able to self-test this entire board. Now, granted that pseudorandom vectors are not good for testing intelligent system like this, but at the board level, remember, your goal is to get chip-to-chip faults. Not your primary concern is if interconnection has failed, or if any driver has gone bad, or things like that. Not quite the internal functionality of any one of these blocks. So for that purpose, pseudorandom vectors are perfectly all right. Also, notice that this is the hardware he employed for using the linear feedback shift register-based self-test for the board. Source linear feedback shift register, sink linear feedback shift register, some kind of go, no-go display, and some kind of a little test program. Now, the question is, regardless of which board you may be self-testing in this fashion, those things you always need. So the thought comes to my mind, why don't we standardize on this block? Can we implement that as a proprietary testability support chip, which may look something like this? I mean, which we will be using something like this, where now again, I have a change of terminology here, but it is applicable to chips as well as modules, as well as system and subsystem. There was an idea like this described in 1984 CICC conference paper. It's called Automatic Polydew Self-Test Processor. And Idea is to provide testability support from a dedicated part. And without saying much on that, let me show you what it may look like. We have, needless to say, we need a generator linear feedback shift register. We need some kind of a RAM here, or RAM or PROM, whatever here, which will know when to apply the test and when to stop the test. We need a linear feedback shift register to get the responses, as well as some kind of a memory here where we would store expected fault-free signatures. Sorry, that's here, signature file. And then some kind of fault isolation register. Now again, the same thing is described pretty well in the paper I referred to. So let's move on. So the next thing comes to my mind is non-intelligent board. At one point I thought maybe I should call it stupid board, but then didn't want to offend anybody, so stuck with non-intelligent board. So here the characteristics are that they are populated by gate arrays, MCAs, and some off-the-shelf components. Strategy here, well, we could try both built-in self-test as well as scan design. But the strategy should be to determine test hooks which may support the SSD is symptom-directed diagnosis, should be really SDD. And also, we may also want to consider putting test hooks on module which would support system-level test and diagnosis. And of course, the test hooks, if you want to implement test hooks cost effectively, the best place to implement them is on the individual gate arrays and MCAs which populate the board, and not by using SSI or MSI components. Well, if they get left out on those gate arrays and MCAs, then you may want to consider putting them with some dedicated testability support chips, and we'll see some ideas about that. So again, in this space, we have examples such as Titan and Aquarius, which are certainly doing like this. Now, the beautiful thing about the linear feedback shift register self-test as well as scan design is that all of them are upward compatible. If you had chips which had scan in them, you could easily pull together all those chain paths at the board level to make it into a board level scan path. And I think same thing goes for built-in self-test. So this slide just emphasizes that. Now, what if your components did not have, gate arrays did not have scan design on them, and you wanted to consider implementing scan design at the board level? Is there a way out? Well, fortunately, yes. Lately, people have been, some manufacturers, chip manufacturers such as AMD and Monolithic Memories Inc., they have come up with these devices with on-chip diagnostics. And what they are, these are the list of devices available today which have on-chip scan register. This one is a writable control store pipeline register. Then there is a registered static RAM, general series 4 wide register PROM, and fuse programmable controller. All of these devices have this structure in them. They have two registers. One is the pipeline register, which you use for your normal system operation. So when you are not testing, the data comes in here, and through this register it goes out back to the system. During testing, you could shift in a test data serially into this shadow register and apply it, then load it to this pipeline register through this MUX. Or you could dump this pipeline register into the serial shadow register and then look at the what was there in the system register serially through this line. So this one here is a 24-pin 0.3-inch package, and they say that it is available. Now, all of the other chips also have the same thing, but in addition to this serial shadow register thing, they would have, for example, PROM here, or the RAM here, or the programmable controller sitting on this at this point. So there is still some way out. If the things got left out at the chip level, you could try them at the board level. Let me tell you one number here. If you were to implement the built-in logic block observer by using off-the-shelf SSI and MSI components, at one time I made an estimate that I would require one SSI or MSI component per bit of that Bilbo register. So if you had 32-bit wide system, 32 bits for linear feedback shift register, forget it. That scheme will never get implemented. So we want to do something about that. And the first thing we may want to consider is localizing the test data sources and sinks and providing the self-test from a central self-test control device. That was if you remember, that was the last slide before the summary in Roy's presentation. What you could do is draw a line here. What is above the line is test data sourcing and syncing, and what is below the line is self-test control. So rather than jumping ahead, okay. So by providing the central self-test control, we could avoid the multiplicity of test hardware, and that can be done at the module level or at the system level. Centralization could be done at the individual modules or even at the system level. And that central self-test control processor could be the console processor of the system, or it could be some dedicated central PolyDiv self-test processor, dedicated testability support chip, and APSP, which we discussed a few minutes ago, was one idea along that line. Now, local test data sourcing and sync are important for the sake of good test effectiveness. And in order to do that, we want to put linear feedback shift registers closer to the function under test. And those linear feedback shift registers must preferably be built on the chips, on the custom chips or MCAs which implement the function under test. That is the most cost-effective way to implement linear feedback shift register. Now, if they get left out from those custom or semi-custom components, then you could still achieve self-test at the board level, provided if we have some general linear feedback shift register chips available to do that. And question then is, well, objective here is to facilitate PolyDiv self-test at the board level, but the questions are, what type of linear feedback shift register should we have? How many stages it should have? At the board level, the life is very general. Today you may have function which is only 8-bit wide. Tomorrow you may have something which requires 12-bit wide linear feedback shift register or 32-bit wide. How do we address that generality? What characteristic polynomial should we be picking for those linear feedback shift register? What should be the various operating modes in this linear feedback shift register? And then again, if we sit down and start addressing each one of those specific needs in specific board designs, then how many different types of chips can we afford to build? There is one answer to all these things, which I would like to call a set of concatenable polydivider chips. And here is a little catalog of these chips. We can think about combining polydivider functionality with normal functionalities for which people use off-the-shelf components at the board level. For example, parity generator checker chip, or a register chip, or even some drivers or buffers and those kinds of chips, which usually come in 8 or 16-bit slices. Can we combine polydivider functionality with each one of these chips? And answer is yes, it should be possible, provided somebody takes initiative and finds good enough application. Now, some of these ideas are my own, okay? And let me tell you, if you find good application, or if you convince me that you would be able to use this type of chip, I think there is funding available to take up the development of these chips. So let me describe two of the ideas here. The first one is called register polydiv or RP chip. It should be well, it is expandable to popular data word sizes, which means 8-bit, 16-bit, or 32 bits. It should be operable as a system register or a scan register or as a signature analyzer, or it could be used even as a test vector generator. And it could be, its applications are in system design. The register part you use for your system operation, and then it could be used as a scan register or even as a linear feedback shift registers for test data source or signature generation or the signature analysis. It could be a 24-pin DIP. The last time I counted the pin, it had 24 pins. Here is another possibility, parity polydiv or PP chip. Again, it is expandable to popular data word sizes. We know that parity function is expandable. You can cascade parity generator checker chips to address however many data bits you may have to handle in your system operation. But by combining expandable or concatenable polydivider and the parity function, we can operate it as a snapshot register or a scan register or as a signature analyzer. And again, applications of this would be in online error checking. Parity part of the chip would provide online error checking, and the scan design as well as bit design together can help symptom-directed diagnosis, which John Chabelle mentioned about, which Roy also mentioned about, and plus we will cover some more of it tomorrow morning in design for diagnosis. Here is an example how it could be used. If we had this is just detailed picture of what that polydiv function may look like. It has several operating modes. It can be operated as a parallel in, parallel out register, or as a generator, or as a compressor, or as a scan register. Okay, just like a Bilbo. And this is just another functional diagram for Bilbo type functionality. But the application of, let me show you the application of PP chip. Instead of, if there were parity checker generator chips on the board, we simply remove those and replace this PP chips in place of those. And we connect them up for the scan operation. On the side, we may have to add some board level logic to give us the feature of symptom directed diagnosis. Supposing we detect a parity error here. Coming from this side somewhere, there is a parity error. At that point, what we may want to do is take the snapshot of the data which came in. Okay, so we capture that is the data which comes in here is the syndrome which may be useful for the field service engineer to come later and analyze where the problem came from. Now, the other part of this expandable idea or the concatenable idea is to be able to put two or more chips together and make them into a larger linear feedback shift register. For example, in the self-test mode, this one would act as a 16-bit linear feedback shift register, whereas each chip alone is capable of acting as an 8-bit linear feedback shift register chip. Is there a question? Now, this idea of concatenation is based on concatenation of primitive polynomials. And again, it is, I have a little paper written up for this. If anybody is interested, he can obtain the copy from me. But this shows some polynomials which have this property of concatenability and various data word sizes you can obtain. To be skipped. So let's take up implementing testability on chips. First, the semi-custom chips. Here the characteristics are that they must, semi-custom includes gate arrays and standard cells and polycells and those design environments. So the principal characteristics is that they have fast turnaround time. obviously test generation and testing time cannot be greater than time required to design those fast turnaround chips. And also they're supposed to be low cost. That means that testing cost cannot be greater than the basic component cost. So here the strategy, again, both built-in self-test as well as scan design are appropriate, but you may find that scan design is generally more affordable. And the way to implement that in any design environment would be to mandate minimal testability requirements. And in fact, this is how they do it at Gator Center. You have to have some basic minimum fault coverage, and I think the number is 98.5. And they don't care how you get it, okay? And in fact, we all should not care how you get it, okay, as long as you can get it cost effectively, whether by design for test techniques or by ad hoc techniques. And then in order to facilitate implementation of design for test, if the designer chose to do so, we should be providing testability design rules, also some testability support macros and cells in the library which is usually available to the designer. And we also should have some in-place CAD support. And we do have some of this in deck, and you will see some of it tomorrow during the CAD session. Now, again, implementing testability on the semi-custom chips, we can think about function-independent test hooks, which may be built on the basic, on the base array. And one such example is CDC and National's on-chip maintenance system, and that is, okay, what about the custom chips? Well, what are the characteristics? They are very complex, requiring long design effort, and speed and performance are so critical that applying any brute force testability is very difficult to justify. Also, I mentioned that fault isolation is usually unimportant once the chips have been characterized and in the mature production stage. Strategy. In general, scan design, at least in DEC, scan design is not considered appropriate to apply at the custom chip level. However, at the last design for test workshop, discussing, during informal discussions with workshop attendees, we found out, Roy and I were chatting with this person from Burroughs. He says that they do implement scan design even on the custom chips. Now then, probing a little further, we found out that the top management in Burroughs comes from IBM. So probably that has something to do with their success with scan design. Okay. So let's say in that, we don't think that the scan design is very appropriate, but some scattered self-test hooks and even scan hooks may be appropriate. Now, the strategy here should be to again exploit inherent features in the design for testability and add test hooks in such a way that not only they help for chip testing, but they live beyond that and can be exploited for system or the module test environment. Now, there are several examples within the deck and even outside deck. Motorola's 68020 has some scattered test hooks. Microvax, CMOSVAX, BIIC, Viper chip, all of them have something along this line. So in summary, scan design offers many advantages in testing during product's life cycle, testing during entire life cycle. Test point flops and scan paths for internal controllability and observability, that's what it is all about, scan design. And that we saw it in the morning, and we saw some specific examples during this afternoon. A complete scan design offers maximum benefits, but incomplete scan design can also provide significant testing advantages at reasonable costs. Built-in self-test offers quick add speed. Remember, we can do only static test here. We have to shift in and shift out between the system operations. So in contrast to that, built-in self-test can offer at-speed testing with minimal test data handling and storage requirements. And linear feedback shift register techniques, they seem to be the most popular one, most practical one. And nothing, you go to test conferences year after year, you still hear people working with these techniques, and not many new techniques have emerged. Not a single new technique has emerged really.